Hi, okay, I'm gonna share my screen and get started. Okay, so I'm gonna be talking about heat capacity and the Boltzmann distribution. And again, like all my information comes from the textbook, so feel free to look there if you want any more resources. So this graph is of a protein that's in a solution of water and being heated slowly. Okay, at the beginning, the heat capacity is pretty similar to the heat capacity of water, but at some point, the heat capacity rises quickly and then falls back, ultimately plateauing at a slightly higher heat capacity than before. And so we're gonna try and explore why this is. So in order to understand that graph of the protein, we first need to try and understand how molecules change with temperature. So, for molecules that aren't an ideal gas, incoming energy can affect the system in two different ways. It can either increase the kinetic energy of the molecules, which will show up as an increase in temperature, or it will increase the potential energy or change the potential energy. So, exciting molecules from lower energy states to higher energy states. So, let's take a look at these pictures. So, first off, what is happening to the molecules in B when they are heated? If anyone wants to say they can, but if not, I can just.
In B, there's a conformational change.
Yeah, exactly. So they're moving from a trans conformation to a cis conformation, which is higher energy. And so will the temperature increase more in A or more in B, given that the same amount of heat is being put into the system?
More in A.
Yeah. So the conformational change that's occurring in B will take up energy. So the increase in kinetic energy or temperature will be lower in B than it will be in A. So now we're going to go back to proteins. And the key to understanding proteins is to recognize how they're held together. So basically, proteins are held together by numerous weak interactions, and this includes hydrogen bonding and van der Waals forces. And so each of these interactions on their own is weak or easily broken, but if you put them together, they can really help stabilize the folded structure through extensive interactions. And the energy required to break these interactions contributes to an increase in heat capacity as the protein unfolds. So if we go back to the graph, we can see that at low temperatures, the molecules are folded and stable. And so heat capacity stays relatively constant because these interactions aren't being broken yet. So most of the energy put in is going towards increasing the temperature of the system. Whereas at higher temperatures, the protein begins to unfold, undergoing cooperative unfolding transitions. So once a small number of interactions are broken, the other interactions become unstable with them. And that's called cooperative unfolding. So why, when this happens, does the heat capacity increase? So more of the energy input into the system is being used toward changes in potential energy rather than changes in kinetic energy. So it will take increasing amounts of energy for the temperature to rise. That correlates to an increase in heat capacity. And then after this, we reach the melting point, which is one important thing to remember. So the melting temperature of the protein refers to the temperature at which it's half folded and half unfolded. And this is also going to be the point when heat capacity is at its peak. And then after the protein reaches the melting point, the heat capacity begins to drop. And this is because less and less energy is being used to break the bonds within the folded protein. And so this energy can go instead towards changing the kinetic energy. So this means that the heat capacity will be lower. And then finally, the heat capacity plateaus at a higher value than it was originally at. And the reason for this is because the protein's no longer tightly folded, it's now unfolded. So there's more room for changes in potential energy or excitation to higher energy levels. Some energy is being used to increase the potential energy, so there's less available to increase kinetic energy, and therefore the heat capacity will be higher. And so now we're going to talk about the Boltzmann distribution. So the Boltzmann distribution, very generally, describes the population of molecules in different energy levels. And to understand this, we need to remember that according to quantum mechanics, we know that energy is quantized, and so only certain values of molecular energies are allowed. This can be seen in energy diagrams where each level corresponds to a different electronic excitation state. And so this is like a pretty basic one right here. And then where you can see like each level is a different energy level. So an atom can either increase its energy by moving faster, which will increase translational kinetic energy, or by converting to an excited electronic state, increasing potential energy. And some molecules can also increase energy level by rotating more quickly or by moving to states of higher vibrational energy. So when we look at this picture down below, it's a triatomic molecule, which means it can rotate and move to higher vibrational energy. And so for each electronic energy level, there's kind of like a subset of energy levels that correspond to rotational and vibrational energy levels. And then what does the Boltzmann distribution tell us? It gives us the probability of finding molecules in different energy levels at a given temperature and at equilibrium. And it's shown through a mathematical expression. So, which I placed up here. And so N corresponds to the number of total atoms or molecules in the system. And Ni is the number of molecules that will be found in a given energy level with energy Ui at equilibrium. Kb is the Boltzmann constant, and this is the value of it. And then T is absolute temperature, and Q is a partition function. And so these are both representations of Boltzmann distribution. So Q, which is the partition function, is a normalization factor, which just ensures the probability of finding a molecule in any of the energy levels is 1. And so this will be explained further later on in the class, like the partition function. And for right now, you can kind of just understand a simpler version of the Boltzmann distribution, which equates Ni to e to the negative ui divided by kBt. And the exponential term is known as the Boltzmann factor. So when we use the Boltzmann distribution, it can help us understand which energy levels will be populated to a significant extent, or what extent energy levels will be populated relative to other at a certain temperature at equilibrium. So this is probably going to be the most useful for us in comparing the population between two different energy levels. So if we want to know the ratio of number of molecules in level 2, which is represented as N2, to the number of molecules in level 1, which is given by N1, we can use this formula, which is just taken by dividing the equation from the last page. And so N2 over N1 equals e to the negative delta U over kBt. And delta U in this situation corresponds to U2 minus U1. One thing to look out for when doing problems with the Boltzmann distribution is making sure that the sign of the energy is correct and like the amount of energy is correct. So, because it's easy to get like flip them when you're doing these kind of problems. And then, so this slide is just some energy levels. And so in A, you can see that these are going to be 3 different molecules at the same temperature. Molecule A has a really large energy gap, B has an intermediate, and C has a low energy gap. And so the higher the energy gap, the less percentage of molecules will be found at that higher energy, because it's more difficult for molecules to get into that state because they have to have a lot more energy. And then once you get to a low energy gap, there's going to be like a much higher percentage of molecules at higher energy levels. And then B is 1 molecule at different temperatures. And so you can see as the temperature increases, the energy of the individual molecules will also be increasing. And so they'll more likely to be at a higher energy level. Okay. And that's it. Does anyone have any questions? Okay, if not, the next tutor can go.
Hey, hi everyone. I'm just gonna share my screen. Can everyone see okay?
Yeah.
Okay, thank you. So today I'll be talking about potential energy and empirical energy functions. So first, what is potential energy? Potential energy is energy that results from the position or the configuration. So in this class, you'll find like lots of different types of energy. You might know about kinetic energy, right? So if I give you a mass, a velocity, you can calculate the kinetic energy. So potential energy is if I give you a position, you can find the potential energy. But in order to calculate a potential energy at a given position, you need to have a reference point that you define where the potential energy is zero. So for the common example, gravitational potential energy, which I think all of you have encountered at least once before, you multiply mass times the gravitational constant times height, that gives you gravitational potential energy. But that gives you gravitational potential energy when we assume that y equals zero has a potential energy equal to zero. We could just as easily define another height where potential energy is zero and then calculate the potential energy relative to that. And similar to spring, right? We define an unstretched spring where potential energy is equal to zero. And then the potential energy with respect to that depends on how much we displace that spring. So in order to calculate a particular potential energy at a given position, you need a reference point. So how do we define potential energy? Potential energy is equal to the amount of work you have to do to move an object from the potential energy zero reference point to the position R, or wherever the next position is. So let's take our gravitational potential energy example again. You have here, this is a diagram in your book. You have this weight on the bottom, and then you have someone pushing it against the force of gravity up a height h. The amount of work it takes to move from potential energy zero to the potential energy at height h is equal to the potential energy. So we can also express potential energy as the negative integral from x0, denoting the position where potential energy is equal to zero, to the point x where you're trying to measure of the force with respect to distance. I think it's important to note that the force in the definition of potential energy is the force exerted by the force field, for example, gravity. The force you must exert to move it must be equal but oppositely directed, and that's the source of the negative sign. The force exerted by the force field always tends towards lower energy and will act to reduce the potential energy. Just as intuitively, right? If you want to increase your potential energy, you have to do work against the force field. If you want to gain gravitational potential energy, you have to work against gravity. If you want to gain elastic potential energy in your spring, you have to work against the spring. And if you let the spring force field or the gravitational force field do gravitational work, you lose potential energy. And if you let the spring do whatever the spring wants to do, you lose potential energy. So let's examine the potential energy of two atoms. So here, consider two atoms that attract each other. So you can see the potential energy in the bottom diagram. The top diagram is the force, which we can get to later. The potential energy decreases in the attractive region, which is this region over here, because you lose potential energy as you move from R equals infinity, where the potential energy equals zero, to R equals R naught, right? So potential energy equals zero at R equals infinity because that's how we arbitrarily define it. So when you move inwards, and this is attractive, you're basically letting the two atoms do what they want. And if you're not putting in work to fight the attractive force that's natural to these two atoms, then you just lose potential energy. But when you get to this region up here, the atoms are so close that they start to repel each other. So to push two atoms closer together, you need to fight that force, and that's why you see this increase in potential energy. So we previously saw that potential energy is the integral with force with respect to distance. If you just divide by -1, differentiate, you get this. You get that force is the negative derivative of energy with respect to distance. So what does this mean? I think the important thing to note is that force is zero when potential energy is at a minimum, right? So if it's at a minimum, you have a well, like we saw before, this well. The tangent for the well is zero. That means dx of potential energy is equal to zero. Your force will be equal to zero. force is also a vector that points in the direction of decreasing potential energies. And we can get this next slide. So I think when I was learning potential energy, it was always confusing to me, right? Like, what does it mean when the force points towards lower potential energy? And I think when I was learning it, I thought that the force vector would be pointing like this, if you guys can see my cursor. But so remember that force is a vector, but this x-axis is distance. This y-axis is energy. Your force vector doesn't point in this plane. Your force vector is just one-dimensional on this line. So imagine you're just a dot on this line, right? So let's say you're right over here. You're at position x something that's positive. Well, this is your potential energy at this position. The derivative of potential energy, so the slope at this point is positive. Your force is negative. So your force will push you this way. So reminder, you're just a dot on this line. So you're getting pushed this way and you get towards this point. Imagine you're on this side, right? So this is your potential energy. It's still positive. And then your force is negative. So it's pushing you this way. And then wherever, if you're on the left side, it pushes you right. If you're on the right side, it pushes you left. So this is what we call a stable equilibrium. And this is essentially this can help you determine what your bond length is. Your bond length is where your atoms have a minimum potential energy, where all the forces are just pushing it towards this particular distance. And we often see these types of graphs, these wells, but you can do this kind of force direction analysis on any given potential energy diagram that you're given. So if I give you this diagram, you can look, at this position, this is the potential energy, the derivative, the negative derivative points a certain way, and you can just track yourself on this axis. So now we're talking about empirical energy functions. So all these relationships between atoms are very complicated, right? You have protons, you have electrons, and whizzing all over the place. So the most accurate way to do this would be to do some sort of quantum mechanic calculation, but I don't know what quantum mechanics is. I don't think you guys know what quantum mechanics is. So to make things easier for everyone, they have empirical energy functions, which are just simplified models of this behavior. So in quantum mechanics, in your book, it says that they have discrete energy levels, which is an assumption. So you can see little dots here, but then when we model it, it's continuous right here. So just long story short, empirical energy functions are just simple ways that we model behaviors rather than deriving them from more fundamental and more complicated equations. So what kind of things can we approximate with empirical energy functions? This is a picture of the annotated slides from your recent lecture. So you can divide the type of energy empirical functions into covalent interactions, non-covalent interactions. You can model the covalent bond distortions by stretching. You can model how the angle between two bonds, rotation around the bond. The point is that you don't have one function for a particular molecule. You have to have different functions that model different behaviors in order to accurately represent those behaviors. So let's think about approximating the covalent bond, right? So at low temperatures, we can use, instead of using a complicated formula that uses the exact positions of the electrons to kind of figure out the force and energies of all the atoms, all the electrons, we can just approximating using Hooke's law. So why can we use Hooke's law? Well, Hooke's law says that if you have, so imagine a spring in a block, right? And it's at equilibrium position. If you push it in a little bit, it pushes back. So that makes sense. If you have two atoms in a bond and you push them closer together than they would like, they're going to try to push each other apart. If you try to if you have a spring in a block and you pull the block away, the spring will try to pull the block back. That also makes sense in a covalent bond, right? If you pull the atoms back, it kind of makes sense that the atoms will want to be forced back together. So that way we can model the covalent bond using Hooke's equation right here. This is just the potential energy, which you can find by integrating this. But there comes a cost at approximating complex equations with simpler equations, right? Because if you look at this diagram, which comes from your textbook, the blue parabola, this is your Hooke approximation. But when you look at the actual energy of a covalent bond, you see that there's this whole thing over here that doesn't at all look like Hooke's law. So what is this? This is what happens to your energy when you break the bond, when your R approaches infinity. This is not modeled by Hooke's law, right? Because if you pull a spring to infinity, your spring is still going to pull back. But in an actual covalent bond, your bond is just going to break. So Hooke's law has a condition that is only accurate for very small displacements, right? Because if you look down here at this red box where I'm circling, you see that the lines match up very well. This means that it's a good approximation. And it's accurate at low temperatures, because at low temperatures, so you have what, 2.5 kilojoules per mole. That's not enough to break this bond. And I can tell that because if you look at the scaling, right, this is 100 kilojoules per mole. So there's nowhere near enough energy for you to get anywhere in this region. So you're just going to be sticking over here, and that's where your Hooke's law is appropriate. And this kind of goes back to the force potential energy diagram I showed earlier, right? This distance from here, where the potential energy is at a minimum, this is your bond length. So that's how you can kind of use energy to determine the actual physical properties of molecules using simplified empirical equations. That's all I have. Oh, actually, just one more slide. You guys were shown a lot of empirical energy functions, and they seem really complicated, and they are. They're the result of Nobel Prize winners. But I think the important thing to kind of get from them is not to focus on the little nitpicky details, but kind of look at the general behavior of the functions. So what does the function look like when R, or whatever variable you're working with, goes to 0? What happens when it goes to infinity? What happens when it approaches a critical constant? If you can kind of look at these things and convince yourselves that, oh, this makes sense. This is accurately modeling what we know, or okay, this doesn't make sense. Under what conditions does this make sense? For example, you can see here for covalent bonds, right? This is the potential energy of a spring, very close. For bond angles, it almost looks exactly the same, except you just replace the name of the variable. So this kind of tells you that there's a sort of restoring force proportional to the displacement. It behaves the same way. For dihedral, so rotation around the bond, you have this cosine factor. Okay, this means that it's cyclical. There's a repetition to it. And you can just kind of see the different decay rates, for example, for your van der Waals energy. Okay, this is a 12, this is a 6. Why is it like this? Does this make sense? So you just look at these things, I think the empirical energy functions will make a lot more sense. But that's all I had to share. Does anyone have any questions? Okay, if not, I'll just hand off to the next tutor. Thank you.
Okay, so I'm going to be talking about the van der Waals interaction. So first, let's just review what exactly the van der Waals interaction is in terms of like physically what's causing the attractive and the repulsive forces that we see. So in all atoms, you have a nucleus surrounded by electrons, and because the electrons are always moving around the nucleus, there can be temporary moments in which more of the electrons line up on one side of the atom than the other, and that creates this transient dipole, which you can see right here, where half the atom is like slightly negative and the other half is slightly positive. And as a result of this like really transient dipole, then all the atoms that are surrounding this atom can also be induced to be polarized a certain way. So for instance, the electron cloud for this atom might shift very slightly in this direction, and this is typically what's referred to as like induced dipole interactions, and that's really just a synonym for van der Waals. And so if we sum all these interactions over the course of like many atoms, or even if we look at just one pair of atoms interacting, we get a graph that looks something like this. And this is called the Leonard-Jones potential, but this is just the name that's given to the empirical energy function for van der Waals forces that you were discussing in class. And so from this graph, you've learned so far in the class and from the previous presentation that the force given is just the negative of the derivative of the potential energy function. So I just want to briefly explore some of the intuition for how you can justify why this makes sense. At least one of the ways that I like to think about it is if I were to place a ball on this graph. And if I were to assume that this potential energy graph is some type of a slope or a hill of some kind, and if I were to place the ball there, I'll just ask myself, what direction would the ball roll in? That's kind of an intuition to understand, why is force the negative of the derivative. And at least from this case, hope everyone can see that this ball is most likely to roll down this direction and kind of just stop right here where it probably won't go anywhere else. And on the flip side, we can also imagine if we place the ball right here, it would probably roll right down and get stuck here as well. But in this case, the ball was rolling in this direction. And we can also plot the tangent lines at these 2 points to see what the derivative of the potential energy function would be. So here's a tangent line at this point. And here we see that the slope of the tangent line is positive. However, we know that the ball rolled in this direction, so that's why the force is ultimately negative, because you have an attractive force. It's pulling the ball towards whatever your arm in is. Additionally, you can plot the tangent line for this point. It's almost vertical, so it's a little bit hard to see. But then this just shows you that the tangent line is extremely negative at this point, and that's why the force is positive, because you have a positive repulsive force that's preventing the two nuclei in the van der Waals interaction from getting too close. And so just the takeaway that I want everyone to have from the slide is just that if we're thinking about the direction that the ball rolls in and its relation to force and potential energy, if the force is attractive, it will be signified by negative, and repulsive for positive. And so next, I'm going to go over a lot of the equations that really govern the van der Waals interaction. So this is the Lennard-Jones potential that I was talking about in the previous slide, and this is just the name that's given to this empirical energy function that you've talked about in class. This is also referred to sometimes as the 6-12 potential because of the 6 and the 12. And the key point that I want to make here is that there are two components of this potential energy function. So there's half of this equation that deals with what is the repulsive force that the two atoms will experience as they're moving closer together, and that's given by this. So here, I got the equation for force just by taking the derivative of the potential energy function and then multiplying by -1. I think the proof is in your lecture notes, which you can refer to, or just do as an exercise for yourself. And then the other component of the 6-12 potential is the attractive component between the two atoms. So as the two nuclei get closer together, what is the change in the attractive force that the two experience, which is given by this. And so in the next couple slides, I'm just going to do a few example calculations with these formulas. And before I move on to that, I kind of want to just do like a quick rundown on some of the units that you should watch out for when you're doing these calculations on, on homeworks or exams. So this epsilon ij term is referred to as the well depth. And if we go back to the previous slide, the well depth is essentially just the distance from the 0 line here all the way to the minimum point. And in a way, this can be thought of as just what is the minimum potential energy that these two nuclei that are interacting, what's the minimum potential energy that they can achieve. And so typically, just to make things easy, I think on homework and tests, it's going to be given as 1 kilojoule per mole. But because it's in units of kilojoules per mole, just remember that joules are newtons times meters, and then force is measured in newtons, so you'd have to divide this by meters, which makes sense because in this formula, you're also dividing by, for force at least, you're dividing by R, which is measured in angstroms, and that's 10 to the -10 meters. So these are just some units that will likely help when you're doing conversions and things like that on homework. So any questions so far? Okay, so next I'll just go over into the example calculation that you did in lecture about the gecko sticking to a surface. So a lot of the assumptions are just pretty much the same that we saw in lecture. So first, we're assuming that atoms are stretched from their optimal van der Waals radii by 20%, meaning that if there is an R min, we're pushing it this way sort of, so that the R min is now 1.2 times R min. And basically we want to know, is the van der Waals attractive force going to be enough to hold up the gecko? Where the gecko, where it weighs 100 grams, and the total contact area between the gecko and the surface is 1 square millimeter. And also we're assuming that the optimum van der Waals radius between the two carbon atoms, which we're assuming is the main surface that's interacting in this van der Waals interaction, we're assuming that this optimum radius is 3.4 angstroms. So the first part of this calculation is all about just kind of asking, okay, what is the net force that the gecko is going to experience if now we're stretching the van der Waals radii to 1.2 R min, so moving from beyond the minimum radius to 20% more. So here is a bunch of equations that details how that's going, but briefly starting from the top right here, well, if you want to find what the net force is, we have to think about the two components that are involved in the 612 potential. So the attractive force and also the repulsive force. So starting with the attractive force, if I calculate F of R prime, and this is R prime is 1.2 times the minimum radius, you get this expression. And if you simplify this a little bit more and you make substitutions in for the units, so here I'm assuming that epsilon ij is 1 kilojoule per mole, and this R min here is 3.4 times 10 to the negative 10 meters, because that's just 3.4 angstroms. And R mins cancel, and so you get this expression. And if you continue simplifying this, you will get this value for the force of attraction between the gecko and the surface, and this is in newtons per mole. And you can do the similar calculation for the repulsive component of the force, and you'll end up with this. And then if you just add up the forces, you should get approximately 12 piconewtons per molecule. And if you follow the numbers for this on your own, you'll see that the numbers are not exactly what you did in lecture, because in lecture you made a few simplifying assumptions, but for the most part, this is roughly how the calculation should follow. And so in the next part, we want to ask ourselves, okay, well, how many atoms actually are interacting between this gecko and the surface? Because the value that we got in the previous part, which is about 12 piconewtons per molecule, is in a per molecule basis. So now we want to figure out how many molecules are actually interacting. And so the way that we make this approximation, as you saw in lecture, is if we're saying that the optimum van der Waals radius is about 3.4 angstroms, then that means that we can take a carbon atom that has a diameter of 3.4 angstroms and basically build a box around it. And that box should have sides of 3.4 angstroms and 3.4 angstroms. So each carbon atom essentially occupies a space of 3.4 angstroms squared, which equals this if you work it out. And again, this is slightly different from what's in your lecture notes, but it should mainly line up. And because 1 square millimeter is 10 to the negative third meters times 10 to the negative third meters, you'll get 10 to the negative 6 meters squared. And this is what you'll end up with the number of molecules. And if you just multiply piconewtons per molecule times the number of molecules, you should get 120 newtons. And then if you ask yourself, what's the force of gravity that's acting on the gecko? It weighs 100 grams, which is a tenth of a kilogram, times the gravitational constant. And so you should get almost less than a newton. So you have more than enough force to keep the gecko stuck to the surface. And this was the thing that you found out in the lecture. And so now I want to do a different problem. So this is a problem that's in the worksheet. And in this question, I ask, what is a fraction of the minimum radius at which the potential energy between two neutral nuclei participating in van der Waals interaction becomes zero due to repulsion? So I'll give everyone just a little bit of time to think about this, but just a few observations. Because I'm saying that the van der Waals interaction becomes zero due to repulsion, remember that the potential energy has to be set to zero. And because R min is experiencing repulsion, you know that your R prime is going to be less than R min. So I'll give people about 30 seconds to think about this, then I'll go over the solution. If anyone has questions, you can also ask them now. Okay, so I hope everyone has at least a little bit of time to think about this problem. So now I'll go over the solution kind of step by step. So like I mentioned for the setup, we have our R prime is equal to X times R min, where X is just going to be some fraction between 0 and 1. So if X is 0.9, then that means you kind of compress R min by 10%. And here we're setting the potential energy to 0. And so if you step through the calculations, this is kind of what will happen. So again, you make the substitution here, and so that allows you to cancel R min, and you end up with this expression. You can divide by epsilon ij, and you end up with this. You multiply by x to the power of 12, and if you simplify, you get x is equal to 0.891. So what's the physical interpretation of this? Because what we just found is that if your new radius is about 90% of what your minimum radius was, then the van der Waals repulsion becomes so overwhelming that now there's no longer an attractive force. So if we're comparing this to the gecko problem, you saw that in the case of the gecko, if you stretch the van der Waals radius by about 20%, you still have more than enough adhesive force to keep the gecko stuck to the surface. But if you compress the radius by just about 11%, then the repulsion becomes so overwhelming that there's no longer an attractive force. And this is kind of just to illustrate the fact that when you're looking at the van der Waals curve, as you kind of separate the nuclei, the drop off in attractive force is kind of slow. But if you try to compress the nuclei, the increase in the repulsive force is very, very strong. And the van der Waals repulsive force is actually very biologically significant because in many of your like polymerases, for instance, for DNA polymerase, for example, as it's adding nucleotide bases, the way that it can detect if a wrong nucleotide has been added in is because of van der Waals repulsion in sort of the active site. And as a result of that, that allows it to correct. So this is just important for that reason and has application to understanding how certain enzymes work. And so really quickly, the last thing that I want to cover is the association between van der Waals and hydrophobic effect. So here's a figure from your textbook. These are meant to be atoms interacting with water. However, let's just pretend that they're residues of a protein. So when you have a folded protein, of course, you have the hydrophobic core, and then you have the residues that are exposed to water. And as a result of that, this only forms because of the hydrophobic effect. And the question that I'm posing to you is, can van der Waals interactions explain why the hydrophobic core of a protein actually forms? And this is something that was, to an extent, talked about in lecture. And overall, the answer is not really. And here are a few reasons why. So when we're considering protein folding, this is an event that requires both an entropy change and also an enthalpy change. And when we're looking at van der Waals attractions, that can only explain some of the enthalpy part. And even then, it's very, very insignificant. But actually, one of the main driving forces for why a protein folds, and this is something that you will probably discuss extensively in future lectures and also kind of like quantitatively look at too. One of the main driving forces for why the hydrophobic core even forms in the first place is because if you have free water molecules in solution, without any other things added in, so like no proteins, no ions, the water molecule can kind of pivot in any direction that it likes because wherever it goes, if the water molecules are arranged in a lattice, they still have access to hydrogen bonds. However, if you add in a protein, especially one that has many, many hydrophobic residues, then all of a sudden when the water molecule pivots to another direction, it loses its hydrogen bonds. And so it kind of has fewer degrees of freedom. So even though it feels like, if you're adding more things to the water, it feels like, intuitively, like, shouldn't that make the entropy increase? But actually, it decreases the entropy because now water has fewer degrees of freedom. And so by packing all the hydrophobic residues of the protein into just one dense core, you kind of preserve the most amount of degrees of freedom for water, that's basically the hydrophobic effect. And again, you'll explore this much more quantitatively in later lectures. But that's all I have. Does anyone have any questions on any of this?
Yeah, I had a quick question. If you could go back to your Hooke's law function slide.
I think the previous two covered Hooke's law, but do you mean the graph?
Yeah, that. Oh, yes, this one. Could you go over again with your slopes, like the concept behind the slopes that you were describing? I think I kind of missed that part.
Sure. So the slope of the tangent line is just the derivative, right? So here at this point, you see that the slope is positive because the line is trending upwards, and here the slope is negative because the line is trending downwards. However, the force that you experience here is just the negative of the slope because this ball is kind of being attracted here, whereas this ball is being like repelled from moving further in that direction, if that makes sense.
Oh, I see. Okay, thank you.
Any other questions? Okay, I'll hand it off to the next tutor.
All right, everyone. So I'm gonna finish off today's session by talking about electrostatics. We'll be going over Coulomb's law, hydrogen bonds, and dielectrics. So let's start talking about Coulomb's law, and just a reminder, we'll be talking about electrostatics, which is referring to charged molecules, but also we'll be talking about today dipole molecules, and specifically dipole-dipole interactions and hydrogen bonds. So just as a reminder, you get those dipoles from the inductive effect because of electronegativity differences. You get partial charges. Now let's talk about Coulomb's law, which we're describing electrostatic energy of an interaction. So if you had two charged molecules, well, how can we quantify the energy between them? And we like to use for Coulomb's law, this may be the form you're familiar with from physics, but rather than plugging in the actual magnitude in coulombs and distance in meters, we like to use elementary charge, which is defined here, just the charge of an electron. And we like to use angstroms. So if you go to page 276 in your textbook, you can look at the derivation, but basically we'll take this equation and we'll get this equation where the charge is up here, you'll plug in elementary charges, you'll plug in your distance in angstroms, and you'll get an answer in kilojoules per mole. So just so you know here, this constant's permittivity of vacuum. We'll talk more about how this constant differs in the vacuum versus water later. But basically, that's what you're converting to get through these equations. That's just what we're talking about. So real quick, when we talk about electrostatic interactions, we usually refer to them in a vacuum. But when we view them in water, those interactions are actually a lot weaker. And in water, that energy decreases by about 80-fold. And just a reminder, for salt bridges, that's between two charged molecules. Those are very important in protein structure and important throughout biological systems. So yes, some reminders. So let's talk about hydrogen bond energy now. So if we look at two charged molecules, and as the distance between them increases, if we were to pull them apart, the energy function will decrease, like the graph -1/r, shown in red here. But if we're looking at neutral molecules, but neutral molecules that have a dipole, the energy will decrease a lot faster, and it's modeled by the graph -1/r³. Why is that? Just because they're not full charges, they're partial charges, right? If they're farther apart, they'll have weaker energy. So as you pull them apart, their energy will decrease faster than, say, charged molecules. And one thing we learned from studying this mathematical model is that orientation really matters for protein conformations. And orientation matters because you get the strongest attraction or repulsion when you have these opposite charges lined up linearly. So that's pictured here. So just negative lined up with positive. So based on that, if we get the strongest interaction, so strongest attraction from them lined up linearly, we'd expect to see that all through biological systems, but actually that's not necessarily the case. And the best example I can find is with beta sheets. Look at antiparallel beta sheets. We find the hydrogen bond pattern is vertical. It's just straight, like we described on the previous slide. But we look at parallel beta sheets, we find those hydrogen bonds are actually the diagonal. So just important to note, in these biological systems, hydrogen bonds have some flexibility in how and where they can form. It's not always just straight linear. It can be diagonal. Now let's talk about how water can weaken hydrogen bonds in proteins. So we know from when we study gases in a container, when we look at stabilization energy, meaning what's the energy difference from when there's no hydrogen bond to when the hydrogen bond forms. Find for that neutral hydrogen bonds, they have a stabilization energy of about 10 to 20 kilojoules per mole. And if this is a charged molecule we're looking at, that stabilization energy is even larger. So this is much larger than kBt, your thermal energy. So it seems that, yes, hydrogen bonds are very strong and would stabilize something a lot. So, but if we study proteins, which are in aqueous solution, we find that most of these hydrogen bonds are constantly shifting. They're shifting from being bonded within the protein to going to bond with water in the solution. So in order for hydrogen bonds to be breaking that fast, they can't be that strong. That energy must be around thermal energy, around kBt. So a lot weaker than if we were just studying this in a vacuum. And so, proteins can form H bonds with itself or with water. That's very important. And the difference between these is very small. So there is some stabilization energy, but really not that much. So why would we have hydrogen bonds to begin with? A couple things here. So of course, it'll make proteins soluble. Without any polar groups, you would have insoluble proteins. It allows proteins to fold. We studied secondary up to quaternary structure for proteins, and hydrogen bonds are crucial for maintaining those structures. And what else is crucial is that competition for water. Because those hydrogen bonds can break really easily, it allows the protein conformation to shift a lot easier. You don't need that big of an input of energy. So that allows, let's say, you have an inhibitor binding and that shifts the protein conformation. That's why that's really important. So though all those biological systems with enhancers, inhibitors, etc., they can function. And important to note, when you look at proteins, we need to satisfy H bonding requirements. When you think about this, that hydrogen bond is not so much important in that it provides like stabilization, but more that it exists. It either exists with water or it exists within the protein. If you had an amino acid missing its H bond, that would really destabilize the protein. And we get that hydrogen bond maintenance from the secondary structural elements for the most part. And this is just on desolvation energy. If you were to remove a charged side chain from water, that's the same idea. If you break that bond, that's a really large energy penalty. So you need those bonds to form. So let's look more on the mathematical side of why this happens. So when you have charged atoms in water, that'll increase the dipole moment of water, which acts to balance the charges in water. But by doing so, that reduces the electrostatic energy between those charges. We can see this modifies Coulomb's law from before. Before we just had the whatever's on the right here with charges in 1391. But now with electrostatic, this is decreased by this epsilon factor, which is the dielectric constant. So this constant has a value of 80 when we're looking at water. In a protein, it's from 2 to 4. And just an important thing to take away from that is the more polarizable the medium, you get a greater decrease in energy. The greater this epsilon value is, the lower the energy. And just note that is different than the epsilon naught that we talked about previously. So what do we get from looking at those models? Well, we get something called the continuum dielectric model, where we replace individual solvent molecules with just a region of dielectric constant. This is just simplifying calculations for us, because if we were to do it without this, we would have to account for every single solvent molecule, and that would be very cumbersome to do all those calculations. So from that model, we can study something called electrostatic focusing, where if we say in water, which for this picture, let's just say is outside of this protein, we have a dielectric constant of 80, and inside the protein, in there, about 2 to 4, we'll find that that means there's stronger interactions because there's a less of an energy decrease. So that can facilitate something like binding. So this basically acts like a funnel near this, I believe it's an active site that was shown in your book. Basically, it'll funnel an inhibitor or a substrate into this site. So that's what we get from using this dielectric model. And yeah, so just really for that, think of it like a funnel. Oh, and I guess the answer's already there. But first question, this is just going over Coulomb's law. Your charge of positive 3 E, that's 0.30 picometers apart from each other. And negative 2 E is the other charge. Calculate the electrostatic energy. You can see the math there. Just plug and chug. I know this should be negative since we have a negative charge here. That is my mistake. Negative 2,000 kilojoules per mole. And just a note on that, just get comfortable as you're going through these next few units. Get comfortable doing conversions from like picometers to angstroms, micrometers, etc. You'll be doing that a lot, definitely. And question 2, I guess I didn't do this right as well, but what level of protein structure helps maintain hydrogen bonds in the folded protein? Just remember that's going to be secondary structure. It's very important for making sure those hydrogen bonds exist in the protein, because without them, you'd have a lot of destabilization. That is all I have for today. Does anyone have any questions? Anything you want me to go over?
I have one question.
Yeah.
For the dielectric constant,
Mm-hmm.
you had 2 equations, one with it, one without. When would we use it with and without?
Yeah, so let's start without. So that's the model for when we're describing something in a vacuum, okay? So if you just had 2 charges sitting in the vacuum, you would use this without, but mathematically that would just mean this epsilon here would be 1, right? So this becomes 1 and you just get this equation. And then when you're not in the vacuum, so if you're in any other environment, you now have this factor, this dielectric constant, that'll increase. So that's why in water you have 80, in a protein it's 2 to 4, it's a different environment, it's something else. But important thing to take away from that is if you're not in a vacuum, the energy of the interaction should decrease by whatever factor you put in there.
Okay, thank you.
Yeah, anyone else? All right, that's pretty good.
Okay, so in that case, I'm going to go ahead and stop the recording, and then I'll hand it off to the tutors for the 6 to 7